Okay. All right, so folks should start trickling in here in just a few seconds. I will give a minute for that to happen, but then we're going to get moving because we actually have quite a lot to talk about today. So let me see if I have a slightly more alive pen. No. Damn, this one's pretty fresh too. I don't know why it's misbehaving already. All right, we're gonna try this. I'm gonna switch to this kind of weird teal color. Hopefully it'll be nice and visible today. A few things. So study guide 2 is out. Sorry I didn't publish this Monday. I got an email last night reminding me, hey, I don't have the study guide yet. And I realized, oh shit, I haven't published it yet. So I put it together last night and it is up now. That of course is due on Monday. And you need to remember to submit the written solutions on Canvas in order to get credit for the study guide points. So the same rules as for study guide and exam 1. Exam 2 is of course going to be on Monday, and we'll be reviewing for that on Friday. But today we're going to cover that last section that's on exam 2, which is section 11.6. And that talks about absolute convergence and root and ratio tests. So I'm going to give you 2 more convergence tests today. And the good news is that they'll be the last 2. So for infinite series, you'll have our result on geometric series, telescoping series and the definition of convergence, the test for divergence, TFD, the 2 comparison tests, the limit comparison test and the direct comparison test, and the integral test. And then after today, you will also have the root and ratio tests, and those will be all of the convergence tests you will learn in this class for infinite series. So let's dive in. Before I can tell you about those tests, I have to tell you what these words mean. So if sigma n from, could be 1 or 0 or wherever to infinity, the absolute value of an, if this series converges, then we say that the regular series without absolute values converges absolutely. So if I tell you a series converges absolutely, what that means is that if you take the terms of that series and replace them by their absolute values, the resulting series is convergent. Also, if the original series, and again, it doesn't have to start at 1, it could start anywhere, sigma an converges, but the absolute value series diverges, then we say that that original series converges conditionally. So these are kind of two different categories within the collection of all convergent series. If you have a convergent series, then it either converges absolutely or it converges conditional. So for all of the series that we have worked with and shown to be convergent, we can go back and revisit them and ask, well, were they absolutely convergent or were they conditionally convergent? And we're going to do a little bit of that here today. The most famous example in this category, or when it comes to this discussion, is the alternating harmonic series. We know that this series converges from last time. And the test we used was the alternating series test. Right, so here the bn's are 1 over n, that is a decreasing sequence, and the limit of the bn's is 0. So this is indeed a convergent series by the alternating series test. Our question is that convergence absolute or conditional? And the common question, a question you'll see on some of your homework and some of the study guide and definitely on the exam, is to categorize a series or a few series as absolutely convergent, conditionally convergent, or divergent. Every series falls into one of those boxes. To answer the absolute convergence question, is the convergence absolute or conditional? We don't play around with the original series, we play around with the absolute value series. All right, we take absolute values inside the series and we ask, is this series convergent or divergent? We know that the original series is convergent. But what about this series that we get by taking absolute values inside? This is where you need to be comfy with the algebra of absolute values. I've said it a few times in this class, absolute values play nice with multiplication and division. So I can take the absolute value of the top and the absolute value of the bottom separately. And since n here is running from 1 to infinity, the n in here is always positive. And upstairs, -1 to the n plus 1, the thing inside the absolute value at the top, is always either +1 or -1, right? -1 to the n plus 1 just flips back and forth from +1, -1, +1, -1, both of which have absolute value 1. And this series, sigma 1 over n, without any alternating piece, this is a divergent p series. It's the regular harmonic series. Here p is equal to 1, which is not bigger than 1. Thus, the original series S converges, but not absolutely. So converges conditionally. So compare the definition above to the work we just did. We know the original series converges, but when we take the absolute values on the inside, the result is a divergent series. So that's the second sentence here. If the original series converges, but the absolute value series diverges, then we say the series converges conditionally. Another important family of examples here, if sigma an, say summed from 1 or 0 or wherever, has only positive terms, then sigma absolute value an is the same as sigma an, because you take the absolute value of something positive and you get the same thing. So any convergent series of positive terms is absolutely convergent. Right? If you're positive, then taking absolute values doesn't change anything. So if you are a series where all the terms are positive and you are convergent, then automatically you are absolutely convergent. It's not possible for a series of positive terms to be conditionally convergent because taking absolute values doesn't change anything. I'd like to do one more example just to get us a feel for the definitions. I'll give you a second for anybody who's still writing. Okay. Let's try to classify the series sigma n from 2 to infinity, -1 over n, or -1 to the n divided by the natural log of n, as absolutely convergent, conditionally convergent, or divergent. Any ideas where we could begin on this problem?
Take the absolute value of the top and the bottom.
We could do that. We could jump right in and look at the absolute value series. Again, we can split the absolute value up, give it to the top and the bottom separately. And because n is running from 2 to infinity, the natural log of n is always positive. The natural log goes from being negative to positive at n equals 1. So for all n bigger than 1, natural log of n is positive. So the bottom is just natural log n. And upstairs, negative 1 to the n, just like negative 1 to the n plus 1, is either positive 1 or negative 1. So his absolute value is just 1. What can we say about this series? Any thoughts?
Oh, it's positive for all terms.
It is, yep, because we got it by taking the absolute value on the inside. So we've definitely ensured that this is a series of positive terms only. What about convergence? Do we think this series converges or diverges? Why?
Converges.
For what reason?
As as n approaches infinity, doesn't it get closer to 0? And so it would equal 0, indicating that it converges.
No, that's not true. So we can run TFD. That's what you're doing there. You're saying the limit as n goes to infinity of the ANs here is the limit as n goes to infinity of 1 over the natural log of n. And that is 0. That's 1 over infinity, which is 0. But this doesn't tell me anything. Remember, the converse to the test for divergence is not true. This is inconclusive. So having the general term go to 0 does not mean the series converges. Now, the test for divergence says if the limit of the ANs is not 0, then the series diverges. But the other way around doesn't work. If the limit of the ANs is 0, we don't learn anything.
Would you use the integral test?
Well, I have a little note here. I don't want to burn too much time on this, but if you can evaluate this integral, then I know many mathematicians who would love to see how. It's actually a very hard integral. Now we're integrating from 2 to infinity, so finding an antiderivative is hard. It's not too hard to show that this integral, I'll tell you, diverges, but it does require some work, and the work that you would need to show that that integral diverges could instead be applied directly to this series. So while the integral test is maybe manageable here, it's not manageable in a way that we would think. Like this is by no means an easy integral. And you'd have to go through that process of showing that the function is positive, continuous, and decreasing, which is a real time sink. So what other tests could we try?
Divergence test, maybe?
Well, that's the one we just did here, right?
Oh, sorry.
For divergence, that doesn't work on this guy. He comes up inconclusive. We've talked about TFD and the integral test. What other tests do we have?
The limit comparison test?
Yeah, we could try either of the comparison tests, a limit comparison or a direct comparison. It's true that you can do this with a limit comparison, but I think the thing that you compare against isn't super obvious. What would we pick for our BNs in a limit comparison here? What do we feel this series is very similar to? I agree with your silence. It's not obvious at all. I don't see anything right away that this series is very similar to, but I do see something that this series is strictly larger than. So the fastest path here is going to be a direct comparison. test, or DCT. The useful fact here is that n is bigger than the natural log of n. In fact, for all real numbers, x is bigger than the natural log of x. All right, here's the line y equals x in the red, and here's the graph y equals ln x in the blue. You see the red is always above the blue. X is always bigger than the natural log of x. So n is always bigger than the natural log of n. And in particular, if you take reciprocals here, 1 over n is certainly smaller than 1 over the natural log of n. And more is true, these things are positive, certainly for all n greater than or equal to 2, which is the n values that I care about here. So if you have a smaller denominator, then you will be bigger overall. Since natural log of n is smaller than n, 1 over the natural log of n is larger than 1 over n. I'll call this inequality statement here star. And since we know that sigma n from 2 to infinity 1 over n is a divergent p-series, here p is equal to 1, which is not strictly bigger than 1, it follows that sigma 1 over the natural log of n summed from 2 to infinity diverges also by star and the direct comparison test. Right, so the terms of this series are larger than the terms of this series. So this guy is bigger than this guy. And if you are bigger than something which is divergent, you must yourself be divergent.
Sorry, quick question, kind of off topic. How
go
many
ahead.
questions are going to be on the exam?
About the same as exam 1, more than 10, less than 20.
Okay.
The structure of exam 2 will be very similar to that of exam 1, just different questions. Are we all comfy with the direct comparison work we did here? Are there any questions about the inequalities we got, or how we got them, or how we used them, or anything that we wrote down? And we're all comfy with why this is inconclusive, right? That's important. So one of the most common mistakes I see is people saying, oh, well, the limit of the ANs is 0, therefore the series sigma AN must converge. The limit of the ANs is very, very different from sigma AN. Here we're adding up all of these terms. Here we're asking what's the limit of those terms? Totally different animals. So misunderstanding TFD is a common issue. And there's almost always on my exam 2 at least one problem, usually a true-false problem, that checks whether or not you fully understand what TFD says. So I would caution you to maybe go back and rewatch that video from last Monday where we talked about TFD. Read in the textbook, section 11.2, where TFD is proved and discussed. Make sure you really understand the statement there, because it's an easy one to mess up. And it's an important thing, so it usually shows up on the test. All right. So what have we learned? Remember what our goal was. We wanted to classify this original series, the alternating 1 over log n series, as absolutely convergent, conditionally convergent, or divergent. Can we say which of those 3 the original series S must be based on this, or can we say anything that it can't be based on what we've done so far?
It can't be absolutely convergent.
Very good. Cannot be absolutely convergent because the absolute value series here diverges. Do we know yet whether it is conditionally convergent or divergent?
No, we have to run the test for that still.
Okay, so what sort of test do we think might be useful to sort out whether this series is conditionally convergent or divergent?
Use AST for the original series.
Very good. We should use AST. The original series here is an alternating series. In fact, if I was doing this, I would have done the AST first. Now, either way is fine. If the absolute value series had come out to be convergent, we could call it a day. But because the absolute value series came out to be divergent, we definitely need to persist alternating series test. So here the BNs are 1 over the natural log of n. And we need to check, are the BN decreasing? And is the limit of the BNs equal to 0? So who can answer the first question for me? Is 1 over natural log n a decreasing sequence?
Yes, because its reciprocal is increasing.
Excellent. Because the natural log of n itself is increasing. Again, this comes from thinking about the graph, right? Picture the graph of ln x. It's always going uphill, never turns around and goes downhill. So natural log n is the sequence stuck along that graph, has to be an increasing sequence. So his reciprocal has to be a decreasing sequence. What about the limit of the BNs? The limit as n goes to infinity of 1 over the natural log of n. What is that? It's actually visible on the page.
0.
Yeah,
Infinity.
0, right? Natural log of n goes to infinity with n, albeit slowly. So this is 1 over infinity, which is 0. So yep, both of these things are true. Therefore, by AST, the series S equals sigma n from 2 to infinity, negative 1 to the n over the natural log of n converges. All right, so now we know that the regular series converges and the absolute value series diverges. So what is true? Which of those 3 boxes does this series fit into?
It's a conditionally convergent series.
Very good. Therefore,
So what would be the why can't you say it's conditionally divergent? Because what is it? The absolute, or is it the absolute value?
well, what would conditionally divergent mean? Now the
That's
series here doesn't diverge, it converges. So to call it any sort of divergent would be incorrect.
Okay.
By AST here, the series must converge. Like this series does have a finite value.
Okay.
But because the convergence isn't absolute, we say it's conditional. There are other ways of classifying series, right? There are ways of looking at divergent series and classifying them into different types of divergent series. And among convergent series, there are many sorts of classifications. But these are kind of the most important 3. So there might be something like what you're thinking, but it's just not something that we discuss in this class. There's no way to take a divergent series, conditionally divergent. How would we interpret that? Like a series that is divergent, but under certain conditions converges. Maybe that would be something like what conditionally divergent might mean. I'm just not aware of any such classification, but something might exist. See Ramanujan's book called Divergent Series, if you want to play around a little bit more with those. All right, it is time for a theorem. And you might be able to smell this one coming. It doesn't have a name, but it just says if sigma an converges, and again, the sum here could be from anywhere to infinity, then the regular series converges. Another way to say this, i.e., absolute convergence implies regular convergence. So if you converge absolutely, then you converge. There's no way to converge absolutely, but also diverge. Absolute convergence is strictly stronger. I'm going to prove this to you because it lets me introduce the most important inequality in all the land. You may have heard this because there's an idiom in English. The shortest distance between 2 points is a straight line. The way to make that concrete is to say in any metric space, the absolute value of x plus y is less than or equal to the absolute value of x plus the absolute value of y. This is a fact called the triangle inequality. And this can be extended using what's called mathematical induction to the statement A1 plus A2 plus A3 plus A4 all the way out to AN. If you sum a bunch of things and then take absolute values, that's always less than or equal to the sum of the absolute values of those things. Oh, a capital N. So to understand the original triangle inequality, I want you to think about it in a few different cases. If x and y have the same sign, are either both positive or both negative, then the left-hand side here is equal to the right-hand side. Try plugging in some numbers. Like if you plug in 1 and 1, then you get over here the absolute value of 2, and over here you get the absolute value of 1 plus the absolute value of 1, and both of those are 2. If you plug in 3 and 5, or pi and 7, if x and y are both positive or both negative, then this and this are equal. But if they have opposite signs, if one is negative and one is positive, like if x is -1 and y is +3, then over here you have the absolute value of 2. And over here you have absolute value of -1 plus the absolute value of 3 is 4. So taking absolute values before adding things up is always bigger than adding things up and then taking the absolute value, which is equivalent to saying the shortest distance between two points is a straight line. If you extend that to this statement, you know, what works for 2 things will work for 3 things, will work for 4 things, will work for n things, where n is any finite number. Then the object on the left is the absolute value of the sum of n from 1 to capital N of an. And the object on the right is the sum n from 1 to capital N of the absolute value of a little n, which you will recognize as partial sums for 2 different series. Sending capital N to infinity, we get that the absolute value of the sum from 1 to infinity of an is less than or equal to the sum from 1 to infinity absolute value an. So if the absolute value series, if this guy converges, then so must this guy. And if the absolute value of u are finite, then so is the thing inside the absolute value. And that concludes the proof. So the series with the absolute values outside is strictly smaller than the series with the absolute value inside, or less than or equal to the series with the absolute value inside. So if your series converges absolutely, that means this series converges. That's the definition of absolute convergence. So if the bigger thing is finite, then the smaller thing has to be finite as well. But if the absolute value of sigma an is finite, then sigma an itself must be finite. In other words, if you converge absolutely, then you converge in the traditional sense, which is what the theorem says. So that's the proof of the theorem. This can be useful in a handful of different ways. First, it helps us understand the categorization system. If you converge absolutely, then you gotta converge. So you can kind of think of splitting series first into two groups, convergent and divergent. And then over here, among the convergent series, you have absolutely convergent and conditionally convergent. And there's no overlap between the two metagroups. Another way that this is useful is in attacking series where not all the terms are positive, but the series isn't alternating. So an important example to look at here, let's investigate the convergence of the series S equals sigma n from 1 to infinity sine of n over n squared. Hamlet, be good, Bubba. Sorry, my dog is licking his paws again. This series has a problem. I'd like to demonstrate that problem to you by going back to Desmos for a second. Don't panic. We're going to come back. The problem with that series is that it's definitely not a series of positive terms. Here are the numerator of the first few. Oh, this is in degree mode, isn't it? All right, radians. The first three terms of that series are positive because sine of 1, sine of 2, sine of 3, those are all positive. But then sine 4, sine 5, sine of 6, those are negative. Sine of 7, sine of 8, sine of 9, positive again. So this is not an alternating series. This is not an alternating series. Since sine n changes from positive to negative approximately every 3 terms, this series is not alternating. But it's also not a series of positive terms. So because it's not a series of positive terms, remember all of your series tests from 11.2 and 11.3 and 11.4 require the series to be positive terms. The integral test says your corresponding function has to be positive, and both of the comparison tests require that the series be of positive terms. The direct comparison test says an has to be bigger than 0. And the limit comparison test says if sigma an and sigma bn are both series of positive terms, then blah, 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 blah. So none of our tests apply to this series because it is not alternating and it's not a series of positive terms. What's worse is it doesn't actually change sign every 3 terms because pi is irrational. There will eventually be a string of 4 terms that are positive. So none of our tests apply. However, we can mess with this series all day. Because by taking absolute values inside, we make it a series of positive terms. This is right. So I could not, I want to make this very clear. I could not jump in and do a direct comparison to the original series. Doesn't work because the direct comparison test requires everything to be positive. However, I can jump in and do a direct comparison with this series or a limit comparison or whatever you want. Because this series is a series of positive terms. Now you could also try the integral test on this thing, but that's not going to be pleasant. It's not monotone, you know, it's not decreasing. But a direct comparison test will do the job here. So now, I know that 0 is less than or equal to the absolute value of sine n is less than or equal to 1, right? Sine itself is bounded between -1 and 1, so its absolute value is bounded between 0 and 1. This implies that 0 is less than or equal to the absolute value of sine n over n squared, which is less than or equal to 1 over n squared. I'll call this star. Sigma n from 1 to infinity 1 over n squared is a convergent p-series. P here is equal to 2, which is strictly bigger than 1. Thus, by star and dct, sigma n from 1 to infinity, absolute value sine n over n squared, which is equal to sigma n from 1 to infinity, absolute value sine n over n squared like this, must converge. So we've shown that the original series S, which is sigma n from 1 to infinity, sine n over n squared, not only converges, but converges absolutely. So here's the solution. So I couldn't attack the series directly. That wasn't an option because none of my convergence tests apply to the original series. But my convergence tests do apply to the absolute value series. And the absolute value series, I was able to show converges using a direct comparison. The terms of the absolute value series, absolute value sine n over n squared, the bottom there is always positive, so these are the same. The terms of that absolute value series are smaller than 1 over n squared. And since the sum sigma 1 over n squared is convergent, the absolute value version of my series must converge as well. And if the absolute value version of my series converges, then the original series converges. More, in fact, is true. It converges absolutely. I want to make a quick note here, and that's that when you write down these convergence tests, do not leave off the capital sigmas. I see people doing this all the time. They just write 1 over n squared is a convergent p-series. 1 over n squared without a sigma isn't even a series, it's a sequence. Now in your study guide, I've put 1 or 2 questions that are meant to emphasize the difference between sequences and series. And I do that because I really want you to remember them and to use correct notation. Do not leave off the capital sigmas when you're writing this stuff. I know your hand gets tired. I know it takes up more space. I know it takes more time, but you've got to write them. If you leave off the capital sigmas, you're not talking about a series, you're talking about a sequence, and they are not the same thing. Okay. Let's talk about these 2 new tests. So we now know what it means for something to converge absolutely. And we've seen a little bit the utility of absolute convergence. There's a theorem that's a little bit beyond the scope of this class called Riemann's derangement theorem that says if you give me a conditionally convergent series, I can pull it apart and glue it back together in ways that make it converge to a different number than it appeared to converge to originally, or even pull it apart into multiple divergent series. So absolute convergence is a nice condition to satisfy. I would love it if all the series I played with converged absolutely. And the next 2 tests happen to have that as their output. So the first one I'm going to show you is the root test. The root test says this. Let S be sigma n from wherever to infinity an, just any old series. Doesn't have to start at 0, could start anywhere. And define L to be the limit as n goes to infinity of the nth root of the absolute value of an. Then, if L is less than 1, S converges absolutely. L is bigger than 1, then the series S diverges. And unfortunately, if L is equal to 1, this is inconclusive. So this is called the root test because you take the nth root of the ANs. The root test is easy enough to prove, so I'd like to show you a proof. I'm just going to prove the first case that if L is less than 1, then the series converges. Suppose L is the limit n to infinity, nth root absolute an is less than 1. Well, then if L is the limit as n goes to infinity, nth root of an, if this limit exists and is equal to L, then for very large values of n, these things are close. Raising both sides to the n power, we see L to the n is very close to the absolute value of an. Right? If you raise both sides of this expression to the n, L becomes L to the n, and the nth root of abs an to the n is just abs an. The nth root and nth power cancel. Thus, sigma L to the n is very, very close to sigma abs an. Really, it's just the tails here. It could be from wherever to infinity, but I'll say the sum from 0 to infinity. So you just sum. Take this expression and sum on both sides. The object on the left here, this is a geometric series. So if L is less than 1, really if absolute L is less than 1, then the series converges. Now by design, L has to be positive. It's not possible for L to be negative. So if L is less than 1, that's the same as saying the absolute value of L is less than 1. And since these things are very, very close to each other, in particular, if this is finite, then this has to be finite also. That's it, that's the proof. So in other words, L is the closest thing to the common ratio for a series that doesn't necessarily have a common ratio. All right. What the root test does is it tells you that your series is most similar to some geometric series, where L is the common ratio of the most similar geometric series. It's neat stuff. I'd like to do an example with the root test, and then I'll show you the ratio test, the other test that we're going to learn here. As always, you're not responsible for the proof, but you are responsible for knowing the statement of the theorem and how to use the theorem. So let's see how to use the theorem. I'll make a quick note here. The root test is a good idea for series that look like sigma a bunch of stuff to the n, where the stuff isn't constant. Right, if the stuff is a constant, then you're looking at a geometric series. Don't fuck around with any of the tests. Just use our result on geometric series. But if you have a series where you've got a bunch of non-constant stuff raised to the n inside your capital sigma, those are the types of series where the root test is most useful, because the root test has you take the nth root of the stuff inside the series, and the nth root and the nth power will cancel.
So if it was like a function inside where this like stuff is, I guess, so like sine over n squared, we could use the root test.
Yep, that is a good example of a series on which you could use the root test. I have a favorite example here. So let's investigate the convergence of sigma n from 1 to infinity 1 plus 1 over n to the n squared. Actually, let me change this plus to a minus. Yeah, let's do it like that. So this is 1 minus 1 over n, all raised to the n squared power. This is the same as sigma n from 1 to infinity 1 minus 1 over n to the n to the n. And the reason this is one of my favorites is because it requires you falling back on something we talked about in section 11.1 when we were dealing with sequences. So let's jump in. Certainly here I do have a bunch of non-constant stuff raised to the nth power. So I will try the root test. The root test says L is the limit as n goes to infinity of the nth root absolute value an, which in this case is lim n to infinity, the nth root of 1 minus 1 over n to the n to the n. All of those things are positive, so I'm leaving off the absolute values. The nth root here cancels with the nth power here. And you get lim n to infinity 1 minus 1 over n to the n. Does anybody know what this limit is?
One.
Looks like it, because this piece is going to 0, and it's like 1 to the n. But 1 to the infinity is an indeterminate form. So here's where we get to check how well you remember the section on indeterminate forms from Calc 1. 1 to the infinity is a particular kind of indeterminate form. It's an indeterminate power. And if you reflect back on the problems in section 11.1 that we did, one of those problems required the use of logarithms and L'Hopital's rule. I'm going to tell you what this limit is. This limit is 1 over e, or e to the negative 1. And that is less than 1 because e is about 2.7. So the series converges absolutely. By the root test. A special limit thing here that you should remember. And if you haven't proven this yet, you should prove it. The limit as n goes to infinity of 1 plus a over n, all raised to the bnth power. This is always e to the a times b. This is a special limit that I will let you use freely on the exam. But if you want to remember it, I strongly encourage that you prove it. The way you do this is by taking natural logs. So you take the natural log of this expression, rewrite it as an indeterminate ratio, apply L'Hopital's rule, then take the limit, then exponentiate. Another special limit that you guys will be free to use on the exam that requires the same sort of work, and I'm showing you these now because they show up in the context of the root test quite often. The limit as n goes to infinity of the nth root of n. This is, in other words, the limit as n goes to infinity of n to the 1 over n. Just like 1 to the infinity is an indeterminate form, infinity to the 0 is an indeterminate form. In this case, it comes out to 1. So these are two important kind of weird special limits that are very time consuming if you don't remember them, that you're allowed to use freely on the test. So if you bump into a limit that looks like this on the test, you're allowed to just tell me, oh, that's e to the ab. So here, a is -1 and b is +1. So we get e to the -1. And you don't have to show work for that step. But you should go through the process of proving this and this at least once. That way you'll remember it. These limits show up often in root test and sometimes ratio test problems. Hey, sad boy, it's okay. I know you're hungry. I'll get you food in a minute. All right. So the next test we need to learn is the ratio test. And once we have the ratio test, your list of convergence tests for infinite series will be complete. The ratio test starts the same way as the root test, more or less. It says, let S be any old series, sigma an, could start at 0, could start at 1, could be positive terms only, could be positive and negative terms, doesn't matter, any series. And define L this time to be the limit as n goes to infinity of the absolute value of an plus 1 over an. So you take the limit as n goes to infinity of a ratio of 2 consecutive terms. Then the output is the same. If L is less than 1, S converges absolutely. If L is bigger than 1, then S diverges. And if L is equal to 1, the test is inconclusive. It turns out that if you run both the root test and the ratio test on the same series, the L you calculate using the root test, this L, will come out to the same number as the L you get from the ratio test. They're both detecting the same sort of thing. In both cases, L is kind of the closest thing to a common ratio that your series may have. But because the algebra is so different, the root test works great if you've got a bunch of stuff raised to the n. The ratio test is great on any series containing factorials. Or factorial-like products. Another quick note, both root and ratio tests are inconclusive on series where an is a rational, I'm out of space, rational function of n. So anything like a p-series. If you have something that looks in any way similar to a p-series, and by that I mean like 1 over n to the p or any fraction of polynomials of n, both the root and the ratio test will be inconclusive on those, not even worth trying. So the ratio test you should use anytime you see a factorial or something that looks like a factorial.
So
The test you should use anytime you have a bunch of stuff raised to the n. No, go ahead.
So on the first note, would you say like if we're taking the limit of this series like n plus 1 factorial over n factorial, like that would work?
So we wouldn't ever take the limit of the series like that, but if you are trying to test the series sigma n plus 1 factorial over n factorial, yeah, then the ratio test would work well there.
Okay.
That particular series, you could also work using the test for divergence, because n plus 1 factorial over n factorial is just n plus 1. And so that would get caught by TFD.
Okay.
But anything containing factorials is a wise move to attempt the ratio test if there's nothing else that jumps out. So for example, if we wanted to investigate the convergence of the series sigma n from 0 to infinity, -1 to the n over n factorial. We actually worked with this guy on Monday when we talked about the alternating series test. We know that this series converges. We actually approximated the value of this series accurate to 3 or 4 decimal places. But if all I cared about was convergence, I can get the result here stronger and more quickly using the ratio test. L is the limit as n goes to infinity, absolute value an plus 1 over an. And in this case, that's the limit as n goes to infinity of the absolute value. Now an here, an plus 1 is -1 to the n plus 1 over n plus 1 factorial. An plus 1 is what you get by taking your an's and everywhere swapping n with n plus 1. And you should do so in parentheses. So like having n plus 1 in parentheses and then the factorial is very different than n factorial plus 1. So anytime you're writing down an plus 1, please put the n plus 1 in parens. It will save you some trouble. And then I need to divide by an, which is -1 to the n over n factorial. So this is my ratio test limit. And initially it looks scary, but things clean up really nice. I'm taking this fraction and dividing it by this fraction so I can leave the first guy alone, flip and multiply the second. And I get absolute value, -1 to the n plus 1 over n plus 1 factorial times n factorial over -1 to the n. And now I can sort of, everything here is being multiplied. You can multiply fractions straight across, so I can sort of shuffle terms around in here. You get lim n to infinity, absolute value, -1 to the n plus 1 over -1 to the n times n factorial over n plus 1 factorial. And this first piece over here, if you divide -1 to the n plus 1 by -1 to the n, you can use this rule that b to the x over b to the y is the same as b to the x minus y, to say that that first piece is really just -1. It's -1 to the n plus 1 minus n. Or you can say there's n plus 1 copies of -1 upstairs, n copies of -1 downstairs. They're all being multiplied, so you can cancel all except for one of them, which remains upstairs. And then we can split the absolute value up over multiplication. So I've got my n factorial here and my n plus 1 factorial here. The absolute value of -1 is 1. 1 times anything is that thing. Also, n factorial and n plus 1 factorial are positive, so I can ditch the absolute values here. And I get lim n to infinity n factorial, which is n times n minus 1 times n minus 2, all the way down to 3 times 2 times 1. That's the definition of n factorial. It's the product of all the numbers less than or equal to n, divided by n plus 1 factorial, which is n plus 1 times n minus 1 times n minus 2, all the way down to 3 times 2 times 1. And you can see that there is a boatload of cancellation here. The n's cancel, the n minus 1's cancel. This whole chunk cancels. So you end up with limit n to infinity 1 over n plus 1. As n goes to infinity, n plus 1 goes to infinity, so that's 1 over infinity, that's 0. Since L is equal to 0, which is less than 1, the series converges absolutely by the ratio test. And that's job done. This business of writing out and canceling factorials is hugely important.
I have a question about that actually. I've
yeah.
been really struggling to understand the n factorial concept. Is it in a certain section, a section of reading, how that works?
Yeah, so if we look in the textbook, oh, let's see, did I close Sumatra? Come on. In section 11.1, they introduced the factorial. We introduced it as a recursive sequence. Yeah, so I think the first problem where they talk about n factorial is here. So the factorial of any number is the product 1 times 2 times 3 all the way up to that thing. Other places where we talk about the factorial, I think that's mostly it. They just introduce it there and then give you a bunch of problems having to do with it. But we talked about it in class on our first day of sequences. And if you wanted to, we could fiddle a little bit more with factorials. If you look at some of these problems, a lot of them have factorials. I think this one was in your homework.
Yeah, I just don't understand the n plus 1 factorial is probably the only thing that's confusing me, how to break that down.
So anything factorial is that thing times that thing minus 1 times that thing minus 2 times all the way down to 3 times 2 times 1. So 2n factorial would be 2n times 2n minus 1 times 2n minus 2 all the way down to 3 times 2 times 1. Or n plus 3 factorial would be n plus 3 times, what is n plus 3 minus 1? It's n plus 2. Times, what is n plus 3 minus 2? It's n plus 1. And you can keep going. You can write as many of these as you want. The next term would be n, and then n minus 1, and then n minus 2, and then n minus 3. And you just go all the way down to 1. So the factorial of any number is the product, that number minus 1, that number minus 2, that number minus 3, that number minus 4, all the way down to 1. In general, if you like it, you can write n factorial in this capital pi notation. It's the product from 1 to n of k, which is just 1 times 2 times 3, n minus 2, n minus 1, n. To take the factorial of something is to multiply all of the positive integers less than or equal to that thing. So like,
Okay, that makes a lot more sense now.
5 factorial is 5 times 4 times 3 times 2 times 1. 10 factorial is 10 times 9 times 8 times 7, all the way down to 3 times 2 times 1. K factorial would be k times k minus 1 times k minus 2, all the way down to 3 times 2 times 1. That sort of stuff, right? Yeah, so you do want to play around with the factorial notation enough to understand it. You may want to go back to the 11.1 homework and see if you can simplify things like 2n minus 1 factorial over 2n plus 1 factorial.
And that, like, I don't want it worked out or anything, but in that particular example that you just gave, the 2n minus 1 over, a lot of stuff would just end up canceling.
Yeah, almost everything. In this case, everything except for 2 terms would cancel.
Okay.
So the denominator here, 2n plus 1, is 2 larger than 2n minus 1, right? So if you start writing out the bottom, that's 2n plus 1 times what's the number right below that? That's 2n. Times what's the number right below that? That's 2n minus 1. Times the number right below that? That's 2n minus 2.
So it'd
All the
just
way
be
down to
1
3.
over 2n plus 1, because the 2n would cancel as well on the top.
Yeah, so this piece right here is 2n minus 1 factorial.
Okay.
So these two would survive. Everything else would cancel. But you should practice with it. There are also some strange, not quite factorial things that you can run into, like 3 times 6 times 9 times 12, and so on. These are not factorials because you're not going up or down by 1 every time. I could say I'm going to end here at 2n plus 1.
Okay.
But you can write these in terms of factorials. This is 3 times 1 times 3 times 2 times 3 times 3 times 3 times 4, right? These are all divisible by 3. I'm sorry, I guess I should end this then at 3n, not 3n, not 2n plus 1. So this would come all the way out to 3 times n. And then you've got 3 times 3 times 3 times 3, n times. This would be 3 to the n times n factorial. So these weird factorial-like products are also things that you can run into when we talk about series. Or 2n times 2n minus 2 times 2n minus 4 times 2n minus 6, all the way down to 6 times 4 times 2. These are not quite factorials, but they're things kind of like factorials. And if you see anything like these in a series, then the ratio test is a good idea, and you will end up having to cancel an expression looking like this. So practicing writing these things out is a good idea. The textbook has so many good problems. Right now, today, we worked through this section, but the study guide, which is up, has a lot more problems. So let me see if I can go a little more quickly here. Root test, ratio test, rearrangements. So any of these would be good problems to work with. And here you see some of these weird products, right? 1 times 3, 1 times 3 times 5, 1 times 3 times 7. This is not a factorial, but it is a factorial-like thing. 21, 22, 23, 24 all have those. If you wanted practice with that stuff, I would recommend playing with some of those. 44 here is a great problem to play with if you want to wrestle with factorials a little bit. So for what values of k is this series convergent? The top is n factorial squared. The bottom is k times n all factorial. 29, you see the root test problem we did. 30 is another good root test problem. And then if you come into 11.7, this is where I grabbed most of your study guide problems. There are plenty of examples of things involving factorials that are not super obvious or factorial-like products. Playing with these would be a good way to check your comfort with the concept of factorials and things that are similar to factorials. All right, I got to get going. We're a little bit over time. I will have my normal office hour this afternoon, but this Thursday I'm going to do some early voting. I have an in-person office hour at 9:45 A031D because one of my other students requested it. So I will be on campus in A031 or some nearby classroom tomorrow from 9:45 to about 10:45 or 11. But then after that, I'm going to go vote. We're going to go do the early voting thing to get that out of the way. So I will not have my normal 12 office hour tomorrow, but I will have another office hour tomorrow online. It'll just be a little bit later. I would love that I could tell you right now exactly what time, but I have no idea how long the voting lines are going to be. So as soon as I get home from going to vote, I will post an announcement letting you know when tomorrow's online office hour will be. But if you want a surefire, I know the time and I can plan it thing, feel free to come meet me physically on campus tomorrow at 9:45. I'll probably be in classroom A25, but my office is A31. And if you come down to that unit on the north side of building A, you'll find me there. And of course, normal office hour this afternoon. So get working on that homework. If you're behind on the homework, you need to get caught up. It's very important. The exam is Monday, and this is the hard test. So you want to make sure you're in good shape for it. Practice now. If you've fallen behind, this is the cutoff. You got to start grinding really hard now. You put in 5-6 hours a day between now and the test. Even if you're still back on 11.1, you can get caught up and be okay. If you are already caught up and you've been following the material, that's awesome. Just keep grinding like you're grinding and you'll be all right. And if you want help with anything, please contact me. Don't hesitate to contact each other. Make sure you're sharing your solutions and checking them with other people. That is it. I hope you guys have a lovely rest of your day, and I will see you on Friday for the review.